We're T-minus 10, 9, 8, 7, 6, 5. We have to go from ready to start. 2, 1, 0. Booster ignition and liftoff of Shuttle Endeavour with NASA's final space station crew compartment that brings a bay window view to our celestial backyard.
Houston, Endeavour, roll program.
Roger, roll, Endeavour.
This is Mission Control Houston. Endeavour's roll maneuver is complete. It is now in a heads-down position on track for its flight to the International Space Station.
The technology behind NASA's space shuttle takeoff, particularly for missions intended to send spacecraft from the USA to Mars, is a marvel of modern engineering, blending advanced propulsion, robotics, and mission planning. While NASA's Space Shuttle program officially ended in 2011, newer spacecraft such as the Space Launch System (SLS), developed by NASA for deep space missions, serve as the cornerstone for Mars-bound missions. This exploration technology has evolved significantly, focusing on long-duration spaceflight, autonomous systems, and the intricate logistics of landing on and exploring Mars. Let's break down the stages and components involved in this journey. 1. Launch Vehicle. At the heart of launching any Mars-bound mission is the launch vehicle. NASA's current workhorse, the Space Launch System (SLS), is a powerful heavy-lift rocket. It is designed to carry astronauts aboard the Orion spacecraft and other cargo required for long-term space exploration. The SLS features a core stage with RS-1T5 engines and solid rocket boosters that provide the initial thrust to escape Earth's gravity. 2. Propulsion Technology. Rocket propulsion is key to achieving the velocities necessary to reach Mars. The SLS uses a combination of liquid hydrogen and liquid oxygen to fuel its engines, which produces the high-energy chemical reactions needed for liftoff. The boosters burn solid fuel, adding extra power in the first 2 minutes of launch. Propellant management is critical because the journey to Mars demands careful balancing of fuel usage for the trip, orbital adjustments, and landing. 3. Staging and Ascent. Once the shuttle clears the thick lower atmosphere, the first stage, or boosters, are jettisoned. This allows the spacecraft to continue its ascent with the core stage, which is still providing thrust. The second stage, usually a cryogenic upper stage, propels the spacecraft out of Earth's orbit and sets it on a trajectory toward Mars. This multi-stage design optimizes efficiency by shedding weight and using specific engines best suited for each phase of the flight. 4. Escape Velocity. To reach Mars, the spacecraft must achieve escape velocity, the speed required to break free from Earth's gravitational pull, about 11.2 kilometers per second. The SLS's massive thrust ensures that the spacecraft reaches this velocity before it enters a trans-Martian trajectory. 5. Guidance and Navigation. Modern spacecraft rely on highly sophisticated guidance, navigation, and control GN&C systems. These systems use inertial measurement units (MUs), star trackers, and GPS to determine the spacecraft's exact position and trajectory during the launch and interplanetary phases. Ensuring that the spacecraft is accurately directed toward Mars requires constant monitoring and adjustments throughout the flight. 6. Robotic Systems. Robotics play a crucial role, especially in Mars rover missions and other autonomous systems designed to explore the Martian surface. NASA's Perseverance rover and earlier missions like Curiosity rely on sophisticated robotic arms, cameras, drills, and spectrometers to collect data and analyze Mars' surface. Robotic systems help perform tasks that humans cannot do in real time, such as geological sampling and searching for signs of past life. 7. Mars Entry, Descent, and Landing. One of the most challenging aspects of a Mars mission is the entry, descent, and landing phase. Mars has a thin atmosphere, making it difficult to slow a spacecraft as it descends. NASA uses heat shields, parachutes, and sometimes retro rockets or skycranes to safely land rovers and other payloads on the surface. The rover Curiosity and Perseverance used a skycrane system that hovered above the Martian surface to gently lower the rover using cables. 8. Deep Space Communications. Once the spacecraft is en route to Mars, communication becomes critical. NASA's Deep Space Network (DSN) provides the infrastructure to maintain contact with the spacecraft over vast distances. It consists of massive antennas placed at strategic locations around the world to track and communicate with interplanetary missions. 9. Power Systems. In space, reliable power sources are essential for long-duration missions. NASA uses radioisotope thermoelectric generators (RTGS) for missions like Perseverance. These RTGS convert heat generated by the natural decay of radioactive material into electricity, providing power in the absence of solar energy, which becomes less abundant as the spacecraft moves away from the sun. 10. Life Support Systems for Human Missions. Future Mars missions, especially crewed ones, will depend on advanced life support systems. NASA is developing closed-loop systems that recycle air, water, and other resources, ensuring astronauts can survive the long journey and live on Mars for extended periods. The Environmental Control and Life Support System is a critical component of this technology, ensuring oxygen levels, cotton removal, and waste recycling. 11. Autonomous navigation and AI. As Mars-bound missions cannot rely on constant human input due to communication delays, spacecraft and rovers use artificial intelligence AI to make autonomous decisions. NASA's rovers can autonomously avoid obstacles, select scientific targets, and even manage power based on available resources, all without waiting for commands from Earth. 12. Artificial gravity and space habitats. For future human missions to Mars, creating environments that mitigate the effects of long-duration spaceflight, such as muscle atrophy and bone density loss, is essential. Technologies under development include rotating habitats that can generate artificial gravity and shield astronauts from cosmic radiation, which poses significant risks during interplanetary travel. 13. In situ resource utilization. Mars missions require technologies that allow astronauts to use resources found on the red planet. NASA is working on ESRA technology, which involves extracting water from Martian ice and producing oxygen from carbon dioxide in the atmosphere. The Mars Oxygen in Situ Resource Utilization Experiment (MOXIE), carried aboard the Perseverance rover, is a precursor to this, demonstrating the ability to produce oxygen on Mars. 14. 3D printing and habitat construction. Building structures on Mars will be critical for long-term missions. NASA is investing in 3D printing technologies to create habitats using materials found on Mars. This technology, known as additive manufacturing, could allow astronauts to construct shelters, tools, and other necessary equipment on a site, reducing the amount of cargo that needs to be launched from Earth. 15. Mars Ascent Vehicle (MAV). To return samples or humans from Mars, a Mars Ascent Vehicle (MAV) will be required. This small, lightweight rocket is designed to launch from the Martian surface and rendezvous with a larger spacecraft in orbit. This technology is critical for sample return missions and eventual human missions to Mars. 16. The future of Mars missions. NASA, in collaboration with private companies like SpaceX, is pushing the boundaries of what's possible in space travel. The ultimate goal is not just to explore Mars, but to establish a sustainable human presence. New technologies, including nuclear propulsion and closed-loop ecosystems, will be essential for reducing travel times, providing life support, and creating a habitable environment on Mars for extended periods. The technology developed for space shuttle launches and deep space exploration is the foundation for this ambitious goal.